The topic of today's lecture is something called the Liskov substitution principle. So the Liskov substitution principle is named after the computer scientist Dr. Barbara Liskov. If you click on that link, it'll take you to the Wikipedia page where you can find out about her life and career. She is a Turing Award winner, still an active professor at MIT. Among her many accomplishments was a language called CLU, which introduced many of the ideas that we've been talking about in the course. So for example, abstract data types, iterators, the multiple return values that you saw in Python, parameterized types or generics in Java, which we'll be studying in the next lecture and for the rest of the course. It used classes with constructors and methods. It also popularized the idea of exception handling. So this one language produced very many features that are commonly used in today's programming languages. The formal definition of the substitution principle, you can find that in the substitutability notebook. The basic idea behind the principle is that subclass objects must behave the same as objects of their supertype. In other words, a subclass object must be substitutable for a supertype object. Ensuring substitutability requires paying careful attention when overriding methods and when designing the subclasses. If your classes obey the Liskov substitution principle, then people can write code according to contracts of the superclass. And that same code will be correct for all subclass instances. So if your superclass has a class invariant, then the invariants of the superclass also apply to all of its descendant classes. Invariants are public features of a class, and thus they are inherited. If a subclass fails to support the invariants of its ancestor classes, that can cause correctly written code to break, which you never want to happen. Right? So the implication here is that you can create a subclass, and then suddenly code that was already written and tested and thought to be correct now suddenly appears to fail because your subclass does not support the invariants of its superclasses. So an example of this is the counter class. Now remember, the counter class has an invariant that says the value of a counter is never negative. And that means someone can write the following class and test it with every possible counter. And it will seem to be correct. Right? So our method here is essentially the isOdd method, right? Which returns true if the counter C has a value that is odd. Now the implementation of isOdd simply takes the value of the counter, divides it by 2, and computes the remainder. Right? If the remainder is 1, then the method returns true. If the remainder is 0, then it returns false. Now, you can argue that this implementation is a poor implementation. The implementation fails whenever the value is negative, because a negative number, take the remainder with any number, the answer will always be negative. Right? So -1 divided by 2, compute the remainder, is -1. So this method fails if the value of the counter is negative. Right? You can make sure that this method never fails by writing it as c.value remainder 2 not equal to 0. However, this code as it's written is correct for our counter class because the counter class guarantees that the value of the counter is never negative. Now, suppose someone creates a subclass of the counter class called descending counter, and the descending counter counts down towards integer min value and then wraps around to integer max value. Now, there are some problems with this class, namely the counter class description says that it counts up, so you've now got a counter that counts down, so that's a bit of a problem. However, the One of the problems it leads to is that the value of the counter becomes negative. Right? It's easy to implement the descending counter class. Right? Furthermore, the class will compile without any issues. So we look at this, the implementation of the descending counter class is as follows. We have a constructor which calls the superclass constructor on the first line, so that's great. Right? We have a second constructor that also calls the superclass constructor on the first line, which is also great. And the advanced method simply overrides, the advanced method is overridden so that the value of the counter decreases by 1 each time the advanced method is called. Now, the value of the counter can obviously become negative in this case. Right? So the method is odd now fails when given a descending counter instance whose value is negative. Right? And so the problem that's occurred is that a class and its method that were thought to be correct suddenly fails when given a subclass that doesn't respect the invariance of the counter class. The subclasses must support the same invariance as the superclass, as all of its ancestor classes, but that doesn't mean that the subclass cannot modify the invariants that are inherited. So a subclass can modify the invariants as long as the modified invariants still satisfy the inherited invariants. Right, so remember what the invariant is for the counter class is that the value of the counter is never negative. So it's possible to create a different type of counter called ranged counter that counts between some non-negative minimum and maximum values. Right, so instead of counting between 0 and integer max value, we could count, for example, between 5 and 10 or something like that. Right, it's easy to implement such a class. Right. The invariance for the class changes. Right now, the invariant is that the minimum value of the counter is always non-negative, and the maximum value of the counter is always greater than or equal to the minimum value. And again, you could implement the range counter class just by extending the counter class. Now, when you do this, this is an example of a subclass where you would want to add new fields to the subclass. Right, so the value of a ranged counter, that field that represents the value, still lives in the counter class. Right, but the ranged counter needs to know what its minimum and maximum values are. So you would add 2 fields here, representing the minimum and maximum value of a ranged counter. The invariant for a ranged counter satisfies the inherited invariant from the counter class because a ranged counter promises that its value is always non-negative. All right, we're now going to look at a different class called the shape class. So the shape class is a superclass for 2-dimensional shapes. It's an example of an abstract class. An abstract class is a class that's not used to create objects directly. So for example, you cannot make a shape object directly by writing shape s equals new shape. Right? The class still has constructors, but the purpose of an abstract class is not to make objects of that type directly. So the purpose of an abstract class is to serve as a superclass in an inheritance hierarchy. In other words, it's a building block for other classes. Right? So the shape class would be the building block for all 2-dimensional shape classes in our hierarchy. In an abstract class, you would declare methods that are common to all of the subclasses. Right? So our shape class is going to declare the methods that all shapes should have. And it declares fields that are common to all subclasses. So again, our shape class will declare any fields that are common to all 2D shapes. When you draw the UML class diagram for an abstract class, the name of the class appears in italics. The description of the shape class reads, It's the superclass for 2D shapes that have an independent width and height, right? So that word independent is important. The width and the height have a minimum value of 1 and a maximum value of 100, right? So in other words, the invariant of the shape class is that its dimensions are always between 1 and 100 units. Right? To create an abstract class, you simply use the keyword abstract, right? And that makes the class abstract. So in other words, you cannot make a shape object directly. Our shape class has two public static final fields that represent constants that are important to the class, right? So those are the minimum and maximum lengths. It has two protected fields representing the width and the height of the shape. The width method for the shape class returns the width. Its contract says that it returns the width of the shape and that the return value is always between 1 and 100. The method area upper bound returns an upper bound on the area of the shape. Now, some shapes have a complicated geometry, and computing the exact area of such shapes is difficult. So the purpose of area upper bound is to return an upper estimate of the area of a shape, right? So in other words, an upper bound estimate on the area of the shape. So in other words, the value returned by area upper bound is guaranteed to be greater than or equal to the true area. Right? The description for the method goes on and says that subclasses should override this method if they can provide a tighter upper bound. Right? And it even says that the method simply returns the value equal to the width times the height of the shape. So in other words, it returns the area of the bounding rectangle of the shape. There's a method called setDimensions, which changes the width and height of the shape. So the contract says it changes both the width and height of the shape to the specified dimensions. It throws an exception if the width or height is outside of the range 1 to 100. Okay, so using the shape class, a programmer can look at the documentation for the class and its methods, and they can produce a method that randomly changes the size of a shape object, right? Furthermore, when they write the method, that method will pass every possible valid unit test, right? So in other words, the method as it's written is correct. So our method's called random scale. It's just going to scale the size of the shape by by some random value. Right? So if you look at the implementation, it computes a new width that's equal to the current width times 1 plus some small, possibly negative value. Right? So if you look at the values here, you can see that this scales the width by plus or minus 0.5% of the current width. Right. Similarly, it scales the height by plus or minus 1 up to plus or minus 0.5%, the percentage of the current height. Right. Now, before calling setDimensions with the new width and height, it checks if the new width and height satisfy the preconditions of the setDimensions method. Right. So in other words, it checks, is the new width between 1 and 100, and is the new height between 1 and 100. Right? If so, it calls setDimensions. Otherwise, it doesn't, right? And does not change the size of the shape. Okay, now suppose someone comes along and creates the class called rectangle, right? So someone makes the subclass's shape to produce the rectangle class, and then they subclass rectangle to produce the square class. This picture here should look familiar to you because this is exactly the is a circle and ellipse problem, right? Except now it's is a square, a rectangle. Right? Many methods, such as setDimensions, place restrictions on their parameter values. Right? So setDimensions requires the width and height to be equal to be between 1 and 100. If a subclass overrides a method, then it must accept all of the parameter values that are accepted by its ancestor classes. Now, what does that mean? It means, well, shape will accept any width and height between 1 and 100, right? And that means that any subclass must also accept any width and height between 1 and 100, right? Furthermore, if a class overrides set dimensions, right, then the method is supposed to set the width and the height and the shape to the specified width and height. Okay, so suppose that square overrides set dimensions so that it throws an exception if the width and height are not equal. Right, so for example, square extends rectangle. Right, the constructor for the square class simply calls the superclass constructor. Right, the implementer then overrides set dimensions, and they place an extra constraint on the width and height. Right? So in other words, if the width is not equal to the height, they throw an exception. Now this makes sense for a square, because a square always has a width and height that are equal. Right? But this adds an extra constraint that's not documented or by the shape class. Right? To change the dimensions of the square, we could write this width equals width, and then this height equals height. However, the set dimensions method that we inherited from shape already does that. If you want to call a method if you are overriding a method and you want to call the overridden version of the method, then the way to do so is to use the super keyword. So in this example, we're overriding set dimensions. We'd like to call the set dimensions method from the shape class. So in order to do so, we use the keyword super, followed by a dot, followed by the method call to set dimensions. All right, now what's the problem with the square class? The problem with the square class is that it causes the random scale method to fail because the random scale method chooses a random width and height a new random width and height for the shape S. Right? With near certainty, math random is not going to return the same value twice in a row. And so that means the width and height will not be equal, which means when you call set dimensions, right, passing in a square for the shape S, right, the square version of set dimensions will throw an exception because the width and height are not equal. So this random scale method, which the original programmer thought was correct, now appears to fail when passed a square object. This slide simply describes the use of the super keyword to call a superclass method. Right? So it turns out that when you override a method, it's often convenient to call the superclass version of the method because the superclass version of the method does a bunch of the work that you want to do anyway. So to call the rectangle version of set dimensions from within the square version of set dimensions, simply use the keyword super in front of set dimensions, and that will call the superclass version of the method. Now, a method can have constraints on its parameters. A subclass that overrides the method cannot add or strengthen the constraints on the parameter values. So, for example, right, in set dimensions, we cannot add the constraint that the width and height must be equal. However, a method can remove or weaken constraints on the parameter values. Right? So, for example, if you wanted to, you could implement rectangle so that its set dimensions method does not throw an exception for out of range values. So in the rectangle class, we can implement set dimensions so that it satisfies its superclass contract, right? So in other words, it changes both the width and height of the shape to the specified dimensions. Right? But now, given an illegal width or height, right, the method can choose to do something other than throw an exception. Right? So this says that the widths or height that are out of range are clamped to min length and max length. Right? So in other words, if you pass in a width that's less than 1, it gets set to 1. If you pass in a height that's greater than 100, it gets set to 100. Right? That's easy to do using max and min. And so now this version of set dimensions does not throw an exception when passed an illegal width or height. It still satisfies the contracts of this superclass because it accepts any width and height that the superclass, that the shape version of set dimensions accepts. Now, methods can also promise something about what values they return, right? So methods also have postconditions. If a superclass method promises something about a return value, then the subclass that overrides the method must ensure that the overridden method returns a value that satisfies the promise of the superclass. Now, so an example, the width method in shape promises to return a value between 1 and 100. Using the contracts of the methods width and height from the shape class, it's possible to write a method that scales the dimensions of a shape object so that its width is equal to 1. We say that such a method normalizes the width of the shape. The idea in the method is that we take the width and height of the shape and we simply divide both of those dimensions by the current width. That ends up setting the width of the shape to 1, and it scales the height of the shape accordingly. It's easy to implement this method as long as the width of the shape is not 0, because otherwise we end up dividing by 0. Similarly, the height of the shape must not be less than the width, otherwise we end up setting the height of the shape to a value less than 1. As long as those two conditions are met, you can easily write such a method, and that method will pass every possible valid unit test that you can write using the contracts from the shape method, method's width and height. An implementation of a method called normalize width would be as follows. We compute the new height of the shape by taking the current height of the shape and dividing by its current width. We then do the same thing to the width, but dividing the width of the shape by its current width would set the width to 1. We then call set dimensions, passing in the width and height. As long as the precondition that the height of the shape be less than the width, set dimensions will not throw an exception. And this is because the shape class has an invariant that the width is never 0. Right? The width is always between 1 and 100. The problem occurs when a programmer creates a class such as vLine, which is a class that represents a vertical line segment having 0 width. This is problematic for a couple of reasons. So reason number 1, having a shape whose width is equal to 0 breaks the inherited class invariant. Number 2, the width method for the vLine class is now going to return the value 0, which it contradicts the contract in the shape method called width that says that the returned width is always between 1 and 100. It's easy to implement the vLine class using inheritance. In the constructor, we call the superclass constructor, and then we set the width to 0. Now that breaks the class invariant of shape. It's easy to implement the width method. We simply return 0 because that's the width of a vertical line, but that does not satisfy the contract for the width method that was inherited from the shape class. Now when somebody calls normalize width passing in a vLine object, the normalize width method ends up throwing an exception. So it fails even though it could pass every possible unit test that you could write given the contracts of the shape class. Many methods return a value. So remember that the return value is part of the postcondition of a method. A subclass is allowed to return a different value in an overridden method compared to its superclass as long as the value satisfies the contract of the superclass method. An example of this would be the triangle class and the method area upper bound. Here is a possible implementation of the triangle class. The method area upper bound returns the actual area of the triangle. We've even changed the contract or the description of the method to say that it returns the true area of the triangle. Right, now remember that in the shape class, the contract for area upper bound only specified that the returned value would be an upper bound on the area of the shape. Now the triangle class is able to compute its exact area, right? It's just 1/2 the width times the height. And so it's allowed, or the method is allowed to return the true area of the triangle. And this still satisfies the contracts, or the contract that it inherited for the area upper bound method from the shape class. Methods that change the state of an object are called mutator methods. If a superclass method promises to change the state of an object in a particular way, then a subclass that overrides the method must also ensure that the overridden method changes the state of an object in a way that satisfies the contract of the superclass method. Now, we already seen an example of a mutator method that does not satisfy the contracts of the inherited version of the method from the superclass. That would be the square class. So in the square class, the set dimension method so far uses the only. We've already seen an example of a mutator method. We've already seen an example of an overridden mutator method that fails to satisfy the contracts that it inherited from the superclass. So that would be the square class, where the set dimensions method throws an exception if the width is not equal to the height. Another example of the set dimensions method in square would be if the implementer tries to fix their method so that it no longer imposes the constraint that the specified width and height must be equal in the following way. In this example of set dimensions, the square class changes the width and the height of the shape, so using only the width parameter. So in other words, it ignores the passed-in value for the height. Now this version doesn't throw an exception, however, it does not satisfy the contracts of the set dimensions method that were inherited from shape, because that contract said that the width and height would be changed to the specified width and height. And this version of the method simply ignores the height. So it's easy to come up with a situation where someone could have written code looking only at the shape class contract of set dimensions, and now their method fails when it's passed a square object. Another example of set dimensions in the square class would be the following. So here, set dimensions is implemented so that it does nothing. So it doesn't throw an exception, which is good. However, it doesn't satisfy the shape contract because it doesn't actually change the width or height of the square. What the programmer has done instead is that they've added their own method called setLength, and setLength changes both the width and the height of the square to the specified length. There's nothing wrong with the setLength method. The problem in this class is that the setDimensions method does not satisfy the contracts of its superclass. And again, it's possible to come up with many situations where code written using the contracts from the shape class fails when passed a square object. So for example, any code that's written using set dimensions that relies on the fact that both the width and height of the shape are changed no longer works when passed a square object, because the square class doesn't actually change the size of the shape when you set dimensions as gulp. In this lecture, we discussed the Liskov substitution principle. Informally, the principle states that a subclass object must behave the same way as a superclass object. In other words, a subclass object can be used whenever a superclass object is required. If a superclass has a class invariant, then all of its subclasses must ensure that they maintain the inherited class invariant. Subclasses can change the invariant as long as the modified invariant satisfies the inherited invariant. If a subclass overrides an inherited method, then the overridden version of the method must accept every value that the inherited method accepts as input. If an inherited method promises to return a value, then every overridden version of the method must return a value that satisfies the contract of the inherited method. And finally, if an inherited method promises to change the state of an object, then every overridden version of the method must also promise to change the state of an object in a way that satisfies the contract of the inherited method.